שומעים אותי? יופי. Hi. So, good morning everyone, and welcome to space. So, 3 AI agents, 1 impossible mission, and no humans in the loop. That's what we're going to experiment with today. I'm going to show you how autonomous AI agents can collaborate, argue, negotiate, and even compromise to solve a problem that none of them could have solved alone. And we're going to do so by going to space. So check out this simple prompt. Plan a mission to Mars, 4 astronauts, 2 tons of payload. Can my AI agent team figure this out together? Let's find out. But first, quick intro to those of you who don't know me. My name is Dror. I am previously from Platformization. Shout out Platformization. And now lead architect at AI Core. Shout out to AI Core. Best team ever. Thank you. In my talk today, we'll cover 2 main pillars. A, how to travel through space. B, how AI agents collaborate and can help us with things like that. Let's start with space. So, why is space so goddamn hard? Here's the thing most people don't understand. Space is not a straight line. You can't just point your rocket at Mars and go. You're launching from Earth, and Earth is a planet that's orbiting the sun at around 30 kilometers per second. Now Mars is orbiting at a different speed, in a different distance, and you're actually fighting gravity wells all along the way. So if you try to fly straight, gravity will just pull you down immediately and you will crash. So every kilogram of fuel you carry is a kilogram that you can't use for payload, such as science equipment or life support. And it essentially becomes a harsh, brutal optimization problem. So how do we solve it? Enters Hoffman transfer. Hoffman is a German scientist who invented this transfer methodology. It's the most efficient way to travel between 2 planets. So instead of trying to fly straight and crash, you need to enter an elliptical orbit, kissing the source planet's circular orbit on one side. See, this is the source planet here, and this is the closest side to it. It's called the perigee, and then you increase your orbit until you get farther and farther away. This point is the farthest point of the ellipse, and it's called the epigee. So now that we have common language, I want you to understand how this maneuver works. So you need to fire your engine basically twice. Once you get into the normal orbit of the source planet, you fire once to leave it and increase your ellipse. Then you fire the engine the second time to slow down and enter the target orbit. This is how Hoffman transfer works. So everything in between, while I just cruise here in orbit, everything in between those 1 and 2 burns is practically free. So we're just cruising basically on orbital mechanics. And this is how Hoffman transfer route works. It's simple, it's elegant, it's efficient, but it also has hard limits. And that's where it gets tricky, because missiles have limited storage space, so they cannot carry endless fuel. So here's where I want you to know about this coefficient called delta V. Essentially, delta V is the single most important number in space travel. It basically measures how much you can change your velocity. And every maneuver in space costs more delta V. You want to leave Earth orbit? That's going to cost you delta V. You want to slow down at Mars? More delta V. You want to slightly adjust your course and correct it a little? Orbital insertion, something you want to change? More and more and more and more delta V. And that's your budget, eventually. And you start with a certain amount of delta V per this space mission, and it's based on your fuel and missile storage and engine efficiency. But once your delta V is spent, you're done. You're stranded in space because, as far as we know, and so far, there are no gas stations in space. So each destination route has a different delta V cost, and basically the farther you go, it costs more. Mars is manageable, and Jupiter really pushes us to the edge of our limits. And one more little thing you need to know about is launch windows, of course. We cannot launch wherever we want because planets are constantly moving, and Mars isn't always in its optimized position for a feasible Hoffman route. So if we want to transfer from Earth, we need to wait for the right alignment. And for Mars, we know that this window happens roughly every 26 months. 26 months, meaning if you missed this window, come back in 2 years. Okay. So brutal optimization problem needs many, many different kinds of expertise. Look at what we actually need to solve here for this nice basic mission. We need orbital mechanics to calculate Hoffman transfers, course optimization, launch windows. We need resource logistics so we can tell how much fuel, life support per astronaut per day, total mass. And we need mission constraints. What is the minimal date for launch? What is the optimal date for launch? What is the space threshold? What is the budget planning? Spaceship threshold, I mean, sorry. And no single expert can handle all of this at once. In NASA, those are different teams entirely. Trajectory people do not calculate fuel budgets. It's not within their skill set. And logistics people cannot calculate orbital mechanics. This is not what they are doing. Both work solely on their own domain, and they talk to each other when concerns collide. So, what if AI agents work the same way? That's what agent-to-agent or A-to-A protocol is all about. The protocol lets AI agents discover each other, delegate tasks to each other, and negotiate solutions together. And it will not happen through rigid, hard-coded workflows the way we do today, but through open conversations. Each agent is essentially a specialist, and it advertises what it can do. Other agents find it, ask for its help, and if constraints collide, they start to negotiate dynamically. The conversation can go in directions, this is important. It can go in directions nobody programmed in advance, nobody premeditated it. They just go somewhere we did not imagine. And the concept is fundamentally different than the way we work today. Today, we write deterministic pipelines or agentic loops that are serving a specific workflow. But what I want us to do is to build dynamic matrices of capabilities by agents. So with this in mind, let's meet my crew. It's consisted of 3 agents, the most basic agents. I mean, of course, I can break it to more and more skills, but the basic functions are agent 001, the coordinator. It's written in Python, and it handles mission constraints. Agent 002, the trajectory agent. It's written in TypeScript, and this is our orbital mechanics expert guy. And agent 003 is the resource agent, also TypeScript, responsible for logistics payloads. And here's the key. The resource agent can talk directly to trajectory agent when constraints collide, and no one ever told them to. It's just baked into their capabilities. Now, let's take a deeper look into each agent's skill. The coordinator, it can validate mission objectives, it knows about crew limits, payload ranges, and limitations. The resource agent, He handles total mass budgets. It knows that our rocket can carry only a maximum of 800 to 1 ton of fuel, depending on deployment. It also knows that life support costs 2 kilograms per astronaut per day. Trajectory agent is our physicist. It's Mr. Deep Science. It computes Hoffman transfers, delta V requirements, launch windows, route optimizations, special space maneuvers that I don't even know about. And it also knows how to optimize trajectories using those special space maneuvers. So these are their published capabilities. Each agent has a JSON card with this set of skills published, and the rest of the world can read it and see what it can do. And that's how they discover and cooperate with each other. All right, enough talk. Let's fly. I'll show you the demo. Please don't fail me, crew. So let's start with Mars. I will plan a mission to Mars. Let me just move to the demo tab right here. There it is. Okay, I took the liberty to start the demo already beforehand, so let's start the conversation right away. Plan a mission to Mars with 4 pilot crew and 2 tons of payload. Watch what happens. Coordinator validates our parameters, discovers trajectory agent, asks for a route. Trajectory computes Hoffman transfer. Coordinator asks to calculate fuel and support. It's calculated. Let's see it. Calculation is happening now. Calculation is done. Okay, this is good. First of all, the demo is working. I did not trust the demo gods, but I'm happy to see that they're fine with me until now. And mission is approved. We can even ask for the Hoffman transfer. This is the mission statement, and we can ask for the Hoffman transfer route visualization. Let's see the trajectory to Mars using Hoffman route. It's right here. Unfortunately, it's not clickable, but here it is. Earth is right here. During launch, Mars is right here. And by the time we complete Hoffman transfer, those planets will meet, and I will enter orbit around Mars. That's cool stuff, right? So, but Mars is the easy one. Everything fits. No drama here. Let's try to go farther. And yeah, does it know? Yeah, let's try to go farther. And now let's try Jupiter. Same crew, same payload, but farther distance. Initially, I tried it to see how it handles errors. I wanted to see what they explain to me when I give them a destination that is too far for them to reach, as I knew my spaceship cannot carry this much fuel. So I input it to the, let's start a new session. I gave the coordinator the new statement. And it starts the same. Oh my God. Okay. Now it gets interesting. Watch the logs. It's trying to calculate. It gets to the result of how much fuel is required. Calling trajectory agent. Oh, wait, it's already optimized. Let's go back and see it slowly. I missed the drama point. Okay. Here is the calculation. Full required is almost 1,500 units. This exceeds capacity. Maximum delta V for feasibility is 11.4. So instead of failing, this is where I expected the error to get thrown back to me, but it didn't happen. It called back the trajectory agent, and you know what it told him? It told him, optimize delta V for Jupiter to max 11.4 kilometers. This is the fun thing about A2A. They speak in open language. They have ask endpoints, not direct tool calling, okay? So everything is open. And this graph over here that you see here is essentially changing for each kind of type of problem that my team gets. So this is graph for Jupiter, probably different graph for Mars, etc. Okay, going back to the chat. So it optimized. It said, okay, I know what I need to do. I got the optimization. Here is the optimized route for Jupiter. And actually, instead of direct Hoffman transfer, what he did here is kind of magical. It planned a Venus flyby. We don't see it right now here in the mission statement, but maybe it explains it here. Let's show trajectory. And then I'll explain to you how it solved it. Oh no. Demo gods are failing me. We'll try again, or I'll show you backup. Okay, lucky we have backup from previous sessions. This was Mars. And this is Jupiter after with the same optimization. And the trajectory was ready here because I was afraid the demo gods will fail me. And there it is. You see what happened? The spacecraft will swing towards Venus, then uses Venus gravity to slingshot outward with extra velocity. And then it will arrive to Jupiter using 30% less fuel and less delta V. And the trade-off, it will just take 50% more time to get there. So that's a nice workaround. And this is exactly what we see in real missions. This is what they do in real missions. So Voyager, Cassidy, Galileo, and all of those used gravity assist or such gravitational slingshot maneuvers to extend reach to even outer and farther planets. And we got here because of two agents that I did not initially program for this. They negotiated a solution fully autonomously, and the resource agent knew its constraints, the trajectory agent knew the physics, and together they did not want to fail. They kept working the solution that I never expected. Frankly, I expected an error. So this part blew my mind, really. And we need to understand what happened here, so let's try to recap this. In a traditional system, there is one code base with one hard-coded, rule-based flow. So when fuel is over capacity, we return error and done. Mission is already failed. But in true A2A architecture, we have specialists that collaborate, just like humans in real life. Instead of pre-scripted paths, you get dynamic problem solving. So in the real world, as we heard before, NASA would have different teams for that talk and negotiate between each other. We want the same design. We want to mimic the same design and have the same tension between our agents. A2A mirrors how real domain expertise work in collaboration in life. And we want our agents to not just automatically report problems, but join force to tackle it together. And when you arrive to design your own A2A system, you will probably ask me, first thing, Dror, how do I know when or how to split my agents? So I can give you 3 hints we can define as rule of thumb. Ooh, thank you. Oh, you didn't see the art. Okay. So 3 rule of thumbs. First is just like in normal service development, service-oriented architecture, we want separation of concerns. So when you want to model this trade-off between different teams by design, let's say speed versus fuel, quality versus cost, QA versus dev, product versus, you get my drift, right? So when you want this attention by design, because you want separation of concerns, this is the first hint or first rule of thumb to decouple the first agent. Second, different security or data boundaries. Let's say one specific agent has access to data that is confidential or PII or something like it. So only this agent has access to this data, and that's a reason to decouple. And third is context limits. A single LLM has a limited context window, so if you're stuffing all of this, orbital mechanics, fuel tables, launch windows, crew regulations, missile thresholds, all of that context to one agent, you're probably diluting the expertise precision. This is what's called context rot. When you give it too much context, it will start missing and dropping balls. So essentially, all concerns cannot be fulfilled equally because of how we know LLMs are built. So, wrapping up, the future of AI is not about smarter models that we keep waiting for. It's about smarter conversations we can start now. What we saw today is a glimpse of that. Agents can tackle unseen open-world problems within their domain, and we don't need to program all of those. Whether it's planning a space mission or solving your next complex business problem, I don't care. The pattern is the same. We want to build specialists that converse openly. That's all, folks. I was Dror. The demo is now open. I will share it in my GitHub and on Slack. Send it to your missions. Try to break it. I broke it just now. And if you want to build your own A2A agent architecture with your team, we're debuting serverless ADK framework with all of these capabilities next week. So please come talk to me and stay tuned on our channels. Thank you all.